Recently, a lady that is recognized and loved by people the world over was forced to undergo a rather extensive facelift. After years of exposure to the elements, Lady Liberty was in need of a little sprucing up. Unveiled to the public in 1886, this symbol that has lit the way to freedom for millions of Americans has stood as a proud beacon for over 100 years. So it came as no surprise that a little elbow grease and polish was in order. What was surprising when the overall infrastructure of Ellis Island was assessed, it was found that the sanitary sewer that was installed 20 years before the statue was still in excellent condition. What is the secret behind a sanitary sewer still in operation after 120 years? The answer is that the pipe used was made of a ceramic material we call vitrified clay. By vitrified, we mean that clay pipe is fired to a very high temperature that fuses it into a hard and permanent shape. The result is that clay pipe is resistant to the harsh, corrosive atmosphere found in domestic, commercial, and industrial sewer systems in much the same way a chemist's glass beaker is resistant to acid. Additionally, its load-bearing capability keeps clay pipe from going out of round in the ground. No other piping material shares these features, which is why clay is the ideal material for sanitary sewers. If clay pipe manufactured at the turn of the century had a single shortcoming, it was in the method of joining the pipe. Occasional leakage and root intrusion were the result of pipe that was structurally sound but had not yet been fitted with today's high-tech prefabricated joints. Compression joints used today have virtually eliminated this age-old problem. As excellent as clay pipe is, the ultimate success of a clay sewer is very much dependent on a team effort. From the manufacturer, to the engineer, to the inspector and the contractor, the success of the job depends upon each member of the team doing his job right and doing it right the first time. Their combined efforts will result in a system that will serve generations to come and will stand as a silent tribute to their vigilance. For any job to proceed smoothly, there must be good communication and cooperation between the contractor, inspector, engineer, and the material supplier. The engineer has developed plans and specifications that are recognized by organizations such as the American Society of Testing and Materials, and it is his intimate knowledge of proper construction practices that will ensure the successful operation of the completed system. Job supervisors should be familiar with good construction practices and have ready access to all plans and specifications. If adverse construction conditions are encountered resulting in deviations, the engineer must be consulted and his recommendations followed. Construction crews across America begin their day in much the same way. Before the first length of pipe can be installed, the excavation of the trench must begin. As worker safety is of the utmost concern, current federal, state, and local regulations must be understood and observed before the first bucketful of dirt is removed. Common methods for establishing pipe alignment and grade are the laser and grade liner. The laser device sends a straight beam of laser light from a unit which has been positioned for proper line and grade to a target. The grade liner is a device that transfers the line and grade data from the survey markers to the location of the invert of the pipeline. As the excavation of the trench progresses, it is important that the trench width at the top of the installed pipe is held to a minimum. Even small increases in trench width will cause a large increase in load on the pipe and could jeopardize the integrity of the system. For example, if a 2-foot trench width is increased only 6 inches, the load on the pipe increases by about 50%. In deep cuts, a narrow step trench or sub-trench may be excavated after a wider trench is first excavated above the level of the top of the pipe. A V or modified V trench may also be used. Due to the unpredictable stability of excavated trenches, trench walls must be supported by a trench box, shoring, or proper sheeting to ensure worker safety. Again, any increase in the width of the trench at the top of the pipe will require a review of the design by the engineer. If a movable trench box is used, pipe already laid must be securely blocked or braced to prevent the opening of pipe joints when the trench box is advanced in the trench. Any water that has accumulated in the trench during excavation must be removed before final grading of the bedding foundation and during all phases of pipe installation. In extreme situations, the groundwater table can be lowered with well points whenever soil conditions permit. They should be placed reasonably close to the proposed trench and sunk to a depth below the elevation of the trench bottom. Several well points can be joined together so that one pump can handle a group of points. Crushed rock or other coarse aggregate is normally required to stabilize an unstable trench bottom. Loss of pipe grade and support can occur when open graded materials are used on sites having fine to medium native sands and a water table which fluctuates in the pipe zone. To prevent movement of the fine sands into the voids of the open graded bedding material, the material may be encapsulated in geotextile drainage fabric. Remember, the finished grade of the sewer will only be as good as the foundation in the trench. The pipe may be laid on a flat or unshaped trench bottom of suitable undisturbed native material, or in the case of over-excavating, on a restored flat trench bottom. When a bedding material is required, the bottom of the trench should be over-excavated and replaced with crushed stone or other angular material to achieve final grade. Approved native material may also be used, but compaction may be necessary to assure a firm base. The depth of the material below the pipe should be at least 1/8 of the pipe diameter, but in no case less than 4 inches. In rock excavation, the pipe should be bedded on a minimum of 6 inches of angular material. Once the bedding is placed, the contractor can make a quick check of the elevation of the bedding material. Bell or coupling holes must be dug so that the load is entirely supported by the pipe barrel, not the pipe bell. The holes should be no larger than necessary to make sure that the pipe barrel is resting firmly and evenly on the trench bottom or bedding material. Care should be taken when handling and lowering the pipe into the trench to prevent damaging the joint material or disturbing trench conditions. Factory-applied flexible compression joints are used to achieve tight lines in today's sanitary sewer construction. Care must be taken to wipe the mating surfaces clean before joining. Lubricate both joint surfaces, line up the socket and spigot, and shove the pipe together with a steady pressure, making certain the joint is completely assembled. For small diameter pipe, this assembly can usually be done by hand. For large diameter pipe, a sling or other approved device can be used to lower the pipe and aid in assembly. For larger sizes, a bar may be used. When using a bar, care should be taken not to damage the end of the socket or coupling. A wood block should be used to cushion the bar pressure. The manufacturer's recommendations for pipe assembly must be closely followed. The engineer has given careful consideration to the selection of a bedding class to meet the calculated trench load. This is why it is essential that the design trench width is maintained and that the bedding material is placed according to the engineer's specifications. Remember, the pipe strength and the specified bedding work together to support the trench load. All of the recommended bedding systems have the same fundamental requirements. Bell or coupling holes must be provided, and the barrel of the pipe must have full longitudinal support. Class D, C, B, and crushed stone encasement systems differ only in the amount of circumferential support required. In simple terms, Class D is achieved without additional circumferential support. However, the ease with which shovel slicing is accomplished suggests that it should be a standard procedure for all classes of bedding, including Class D. It takes little time, assures that the pipe will remain true to grade, eliminates voids beneath the pipe, and in the haunch areas consolidates the bedding where it is needed most and adds little or no cost to the installation. To be most effective, shovel slicing should be done before the bedding is brought up to the spring line, preferably when it is no higher than the quarter point of the pipe. Once the pipe is laid and the bedding sliced, it is a simple matter to increase the bedding to the quarter point, which gives a Class C bedding. Increasing the bedding to the spring line of the pipe provides a Class B system, and when the bedding is brought to the top of the pipe, a crushed stone encasement is achieved. For clay pipe, it should be noted that extra bedding placed above the top of the pipe is expensive and unnecessary for supporting the pipe. The initial backfill may be of any native material free of large stones or other material that could damage the pipe. Fittings should be positioned and supported by carefully tamping the bedding around and under the haunches to avoid shear failure through backfill load. Some designers use concrete in place of bedding. When concrete is used, it should terminate at the face or edge of the bell or coupling. Risers should be installed so they are supported by the trench wall. Freestanding risers should be avoided unless special construction methods designed by the engineer are used. In cases where fittings or stub-outs will not be connected immediately, a suitable stopper should be securely placed in the fitting and externally braced for additional restraint. This resists the total force against the face of the stopper when air or water testing the sewer line. After the specified bedding material is placed to a height required by the bedding class, the initial backfill is then carefully placed to a height of about 12 inches above the top of the pipe. This is done to maintain pipe alignment and to protect the pipe from damage during final backfilling. Final backfill is normally done in layers. A front-end loader or bulldozer is used to push the spoil back into the trench at an angle so that impact on the pipe zone is minimized. This material should not contain large boulders or lumps that might damage the pipe or disturb pipe alignment. The engineering specifications may call for compaction of the final backfill material. All methods of compaction used to achieve the specified density should be approved by the engineer. If the soil permits, adequate compaction may be obtained by careful water flooding. Many authorities consider it impractical and unnecessary to compact backfill materials to a density exceeding the density of the native trench material. Higher densities to prevent settlement of the ground surface should be limited to the top 2 or 3 feet of fill. Handheld and walk-behind vibrators and small trench rollers are examples of compaction equipment which may be used within 5 feet of the top of the pipe. There should be a minimum of 5 feet of cover over the top of the pipe before any heavy mechanical compaction equipment is employed. This will tend to reduce dangerous impact loads on the pipeline. The selection and use of compaction equipment must be made with care so that the pipe will not be disturbed or damaged. A pavement-breaking type of falling weight stomper or drop hammer should never be used for compacting, even with a substantial cover over the pipe. Service lines are an important part of the overall sewerage system and should be constructed with the same care as mainline sewers. Local pipe manufacturers may be contacted for information on tapping. Manholes should be installed on an unyielding foundation. Settlement of the manhole can cause shearing of the adjacent pipe. Short stubs with flexible compression joints or flexible rubber seals should be used in the manhole walls to allow minor differential settlement to occur without pipe damage. Inspectors are an important link between the engineer's design and the completed project. The inspector must be familiar with the job specifications in order to assure that the requirements are carried out. The inspector should maintain a complete log of all occurrences incident to the construction. Among the important items noted by the inspector are the precise locations of all sewer connections by station and depth, which are later transferred to the permanent records of the project. The testing of a completed sewer line is proof positive that the materials selected and the installation procedures followed will provide years of uninterrupted service. It is a wise practice to test early rather than waiting until the entire project has been completed. Air testing is the most common test method. Because of the structural advantage of rigid clay pipe, this is the only test required. When pipe is installed below the groundwater table, a hydrostatic infiltration test may be the most appropriate. The long-term efficiency of a sewer system depends on the combined efforts of a four-way partnership consisting of the engineer, inspector, contractor, and manufacturer. Each one is important. Each participates in a different but significant way to bring about the desired result, a result that is permanent and a credit to those that had a part in its success. Gravity sewers need not be tomorrow's infrastructure headache. Properly installed clay pipe sewers are as close to being permanent as any product can be. While clay pipe may not be as inspirational as Lady Liberty, Their selection and proper installation will ensure future generations full value for decisions being made today. One day, a future generation will look back at today's vitrified clay sewer system and say, they built it to last.